Section 1 Introduction. We're going to delve into the world of large language models, LLMs, which have shown remarkable capabilities in generating high-quality text and solving a variety of language tasks. These models are trained to predict the next word in a sequence using vast amounts of text and computation. However, it's been found that creating text with a high likelihood doesn't always align with human preferences for different tasks. If not properly aligned, these models can produce unsafe content with harmful consequences. Aligning LLMs can also enhance their performance on other tasks. One way to address this alignment issue is through reinforcement learning from human feedback, RLHF. This approach uses human preferences to learn a reward model, which is then used to fine-tune the LLM using a reinforcement learning objective. However, this method often relies on online reinforcement learning methods, which can be computationally expensive and prone to reward hacking. An alternative approach is offline reinforcement learning, which learns from a fixed set of examples and is more computationally efficient and less susceptible to reward hacking. However, the quality of the policy learned offline is heavily dependent on the quality of the offline dataset. Therefore, carefully curated datasets are crucial for the success of offline reinforcement learning. In our work, we propose a method called reinforced self-training, ReST, which frames the alignment problem of a language model as a growing batch reinforcement learning problem. This method includes two loops: an inner loop to improve the policy on a fixed dataset, and an outer loop to expand the dataset by sampling from the latest policy. Our method offers several advantages over typical RLHF methods. It significantly reduces the computational burden compared to online reinforcement learning. The quality of the policy is not restricted by the quality of the original dataset, and it's easy to inspect the data quality and potentially diagnose alignment issues. We've tested our approach on machine translation benchmarks, a sequence-to-sequence learning problem where the context for conditioning is a sentence in a foreign language. Our experiments show that our method significantly improves reward model scores on test and validation sets and generates higher quality translations according to human raters. Now, let's get into the technical details. A conditional language model produces an output sequence of words given a context or source input, where the words belong to a chosen vocabulary. A language generation policy in an autoregressive model is characterized by a conditional probability distribution. The data distribution is denoted by P, X, Y, equals P, X, P, Y, X, and a given dataset consists of samples from this distribution. The supervised policy is trained by minimizing the negative log likelihood, NLL, loss. We refer to the model that is trained with the NLL loss as behavioral cloning, BC, following the reinforcement learning literature. Section Summary. Large language models, LLMs, have shown impressive text generation abilities but often lack alignment with human preferences and can produce unsafe content. Reinforcement learning from human feedback, RLHF, methods address this by using human preferences to fine-tune LLMs. However, online RL methods used in RLHF have computational limitations, while offline RL methods are more efficient but depend on carefully curated datasets. In this paper, the authors propose a method called reinforced self-training, ReST, that combines online and offline RL to align LLMs with human preferences, resulting in improved performance and reduced computational burden. Section 3 Reinforced Self-Training, ReST. In this section, we introduce a reinforced self-training, ReST, method, which is a reinforcement learning from human feedback, RLHF, algorithm. This method aims to align the outputs of a language model with human preferences. We model human preferences over sequences using a learned reward function. In the underlying process for conditional language modeling, the states are the partial sequences, and the actions are the generated tokens. The ReST algorithm separates the growth of the dataset and the improvement of the policy, which are usually part of a typical RL pipeline, into distinct offline stages. We begin by training an initial model to map input sequences to output sequences on a given dataset of sequence pairs using a specific loss function. Next, we have the grow step, which creates a new dataset by augmenting the initial training dataset with samples from the model. The inputs for this step are resampled from the original dataset, similar to self-training. However, if we have access to the distribution of the inputs, we could sample directly from it. For instance, if we have a model that generates an image from a textual description, the distribution of text inputs can be sampled from a language model. Following this, the improve steps use the new dataset to fine-tune the policy. We keep the original dataset in the training mixture to ensure that the policies do not diverge. We then provide a probabilistic interpretation of the improve step. We consider a specific loss function, with the parameters of the model from the last grow step, the proportion of data sampled from this model in the new dataset, and a single step of growth. The expression for the gradient in this case has two main terms. The first term is similar to an online policy gradient term at the beginning of training, with a specific function replacing the state action value function. The second term considers the original data, but we still ensure that it passes a certain threshold. This term is a form of offline policy gradients which prevents the policy from moving too far from the original distribution, which could lead to model collapse. We then compare this approach with self-training techniques and provide a population interpretation of ReST. In the next section, we explore how the choice of loss, filtering function and threshold, and synthetic data generated by language policy via sampling empirically affect the performance of the resulting policies. We chose machine translation as a testbed for ReST as it is a significant application of conditional language modeling where established reward models are available. We ran experiments on two common benchmarks, as well as an internal benchmark dataset. These datasets contain a set of sentences in the source language and the corresponding human reference translation. We selected a different language pair for each dataset to test the generality of the results. We used a state-of-art reference-free reward model in our experiments, which outputs a numerical score for a given source text and a proposed translation. We report results in terms of average rewards on samples generated by a policy on the validation set. We also experimented with other scores, and ReST improved those scores as well. However, we noticed that an online algorithm can learn to exploit the weaknesses and biases of these two metrics quickly, which can cause the model to generate samples that maximize the rewards but deteriorate the quality of the model's output. For the details of the datasets and models, we refer to the appendix. We also indicate the size of the datasets by reporting the number of samples per source sentence generated at each grow step. Section summary. The section describes a RLHF algorithm called ReST that aligns a language model's outputs with human preferences. It uses a learned reward function to model human preferences and decouples dataset growth and policy improvement into separate offline stages. The algorithm involves training an initial model, creating a new dataset by augmenting the initial training dataset with samples from the model, and using this dataset to fine-tune the policy. Section. Nomenclature. Let's break down the complex concepts in the given text. We've developed different versions of a method we call ReST. Each version is named based on the type of loss it experiences, the number of grow steps it takes, and the number of improve steps it takes. For instance, a version named gold G equals 1 I equals 2 inches has 1 grow step and 2 improve steps. When we talk about standard supervised learning, we're referring to a version of ReST that doesn't take any grow or improve steps and is trained only on the original dataset. If we don't specify the type of loss, we're using the BC loss, which is a common method used in training language models. In our graphs, we've used gray to represent supervised learning and various shades of purple to represent different versions of ReST. We've tested ReST against several different offline reinforcement learning methods, including offline actor critic, OAC, behavior VMPO, BVMPO, and generation by off-policy learning from demonstrations, GOLD. We wanted to see if adding more improved steps to ReST would increase the reward model scores. To do this, we tested ReST on 3 different datasets, using the BC loss function and increasing the number of improved steps. We normalized the range of rewards for training between 0 and 1. We also wanted to see if adding more grow steps would improve the reward model scores. We found that adding an extra grow step did improve performance on 2 of our datasets. We also compared ReST to supervised training. We found that different versions of ReST significantly outperformed supervised learning, even after just the first grow step. This was true across different datasets and language pairs. We also looked at which loss function was best for a single step of ReST. We found that the BC loss function performed the best. We also tested whether ReST could be improved further with a technique called best of n sampling at inference time. This technique generates n samples which are then ranked by the reward model, and the top-ranked candidate is selected. We found that ReST's performance improved with both n and the number of improved steps. Finally, we compared ReST to an online reinforcement learning algorithm called PPO. We found that ReST with multiple improved steps achieved significantly higher rewards than PPO when given the same amount of training data. In conclusion, our method, ReST, shows promise in improving the reward model score without deteriorating the performance on other metrics, suggesting that it may be a more efficient approach than other online reinforcement learning methods. Section Summary. The section discusses the nomenclature used in the paper, including the naming convention for different variants of the ReST algorithm based on loss type, number of grow steps, and number of improve steps. The results show that multiple improve steps in ReST significantly increase the reward model scores across different datasets. Additionally, ReST outperforms supervised learning and achieves higher rewards compared to online RL algorithms like PPO. Section 5. Related works. In this section, we'll discuss related works and how they compare to our proposed method, which we've named ReST. Recently, there's been a surge of research on self-improving alignment algorithms for language modeling. We've compared ReST with several other methods, including supervised learning, self-training, and both online and offline reinforcement learning, RL. Our findings show that ReST is not only efficient in terms of computation but also effectively utilizes exploration data and rewards. Let's delve into some of the specific works related to ReST. Firstly, self-training is a well-known semi-supervised learning method that uses unlabeled data to enhance a model. It's been successfully used in various tasks, such as image classification, protein folding, and several language tasks. The improve step of ReST is similar to self-training. However, ReST differs in that it generates synthetic exploration data for training with RL during the grow step. Next, expert iteration, A, is an RL framework that uses a planning mechanism and divides the RL problem into two parts, planning and generalization. Like ReST, A uses the policy to generate data and learn a policy with RL. However, ReST doesn't require a planning mechanism and uses iterative improve steps to better utilize the collected data. There are also methods for reasoning with language models. For instance, the STAR technique iteratively uses a small number of rationales to fine-tune the model. Another method learns to solve math problems using learned reward models. A recent method, impossible distillation, generates datasets for large language models by sampling from a suboptimal model and filters out low-quality examples. This method is similar to ReST, but ReST can be trained with any offline RL losses and can handle continuous valued reward scores. Moreover, ReST can perform iterative policy improvement on a fixed dataset with the improve steps. Iterated learning, IL, is a process where an agent learns its behavior by observing another agent's behavior. This approach has been used for interactive language learning using deep learning. However, IL differs from ReST as it operates in a multi-agent setting and doesn't use RL. Self-imitation learning, SIL, is a policy for an off-policy actor-critic algorithm where the policy tries to replicate the agent's good behavior. SIL does this by filtering out unsuccessful trajectories from the replay buffer and training the agent only on high reward trajectories. In this sense, ReST is similar to SIL-based approaches. However, ReST is not tied to the underlying RL algorithm used to train the policy and doesn't require a value function to filter out unsuccessful trajectories. Also, ReST is applied to generative AI settings, which don't require interactions with an environment in an online manner. Reward ranked fine-tuning, RAFT, is another method that was proposed concurrently to our work. RAFT can be seen as a specific case of ReST that uses only one improve step for each grow step. The authors reported improvements over BC and PPO on a variety of language modeling and image generation tasks. Our experiments with ReST showed that multiple improve steps with an increasing filtering threshold for one grow step lead to further performance improvements. In conclusion, ReST is a simple, flexible algorithm with minimal hyperparameters to tune. It works well with many designs of grow and improve steps. We've tested ReST in machine translation and found it to be robust. However, improvements in reward model scores don't necessarily reflect human preferences since the reward model is only a proxy for human preferences. To overcome this limitation, the reward models could be fine-tuned on the subset of D_G, annotated with human preferences. We also note that the risk of overfitting to the reward model increases with the repeated iterations of the grow steps. Therefore, addressing this issue is crucial, especially in cases where multiple grow steps are needed to train the model. ReST could benefit from better RL exploration strategies at the grow step, such as MCTS. The ability to exploit the generated data during the grow step could result in a broader exploration of the state action space and better generalization. In summary, ReST is a general and efficient approach that can be applied when a robust reward model of human preferences is available and we can generate samples from the model at scale. Thus, it can be applied to many tasks within the language domain, such as summarization, turn-based dialogue, and other generative audio and video models. With several avenues for future exploration and applications, we believe that ReST is a useful growing batch RL methodology for RLHF. Section Summary. The paper introduces a new algorithm called ReST, which is a compute-efficient approach for self-improving alignment algorithms in language modeling. It combines elements of self-training, expert iteration, reasoning with language models, iterated learning, self-imitation learning, and reward-ranked fine-tuning. The algorithm is flexible, requires minimal hyperparameter tuning, and can be applied to various tasks within the language domain. Section: Acknowledgements. Acknowledgements. We express our heartfelt gratitude to the machine translation teams at Google and Google DeepMind. Their valuable insights during the brainstorming stages and their assistance in establishing the codebase on which this project was built were instrumental. We also extend our thanks to Matt Hoffman, Bobak Shariari, Tylon Seamgil, and Chris Dyer for their engaging discussions about this project. We appreciate Bilal Pio's constructive feedback on an early version of this paper. Lastly, we acknowledge and thank the creators of various frameworks we utilized during the project, including the DeepMind JAX ecosystem and Launchpad.